Okay, so I'm going to start with something that Pierre and Lou did talk about, which is natural extensions. So I want to go over it again, and this time I will concentrate more on the expansions I was talking about. I will go back to continuous fractions at the end, just to show you another applications, because as he mentioned, one of the things we like to why we like to look at natural extensions is to get invariant measures, but sometimes you can get more information. And then after that, I will go to beta expansions and talk a little bit more about what I call random beta expansions, so algorithms that generate all of them. So let me start again with the natural extensions. I will write down the definition, and then one of the items that Pierre mentioned, I will translate it in another way. And so let me just start again with the definition of the natural extension. And basically, we want to talk about natural extensions of systems that are non-invertible. So let me just write down here, and I'll start like this: an invertible measure-preserving system let me call it xf mu t. So t is invertible here, is A, and I'm using the word A because there are many, but they are all isomorphic, is a natural extension of the non-invertible system so your starting space is really the Y space, and it's not invertible, and you want to make a invertible system out of it. If we have the following, if there exists a measurable map, actually it's surjective, and all statements are almost everywhere. Let me call the map C from X to Y, such that a number of properties hold. And basically, some of them are translated by saying that this diagram commutes. So the X sits on top of Y, and here's T, and here's S, and here's C. Such that the first thing is that this diagram commutes, so this means that CT is SC. And basically this says that T orbits are sent to S orbits. And the second one, the measurability of C, of course, preserves the sigma algebras, and this preserves the orbits. And the second one is that the measures are preserved. So here we have the measure nu. Some parts don't write. And here we have the measure mu, and basically nu is the projection of mu. So nu is equal to mu of C inverse. So to measure things down, you can measure them via nu, or you can lift them up, see them in the X system, and use mu. And the third one, Pierre did it like this. It's actually saying that X is the smallest invertible system containing Y. And he made such a drawing. So here's your X, and here was Y, Y. And suppose I have another invertible system, Z, that has properties 1 and 2. So I have another map, surjective map from here to here. Then, in fact, X is a factor of Z, like this. He drew this map. So I'm going to translate this smallest structure by as a statement on sigma algebras. And basically this says that the sigma algebra on the big space, which is F, can be obtained by first lifting the sigma algebra on the smaller space, that of Y, so it's the G, and then I lift it up, so it becomes a subsigma algebra of the one up, but this is not enough. Then I move things around via my map T, and I take the smallest sigma algebra containing all of these. So it looks like an ugly structure, but basically this tells you that F is the smallest system that or X is the smallest system that contains Y. Okay, so this is the definition of a natural extension, and as he mentioned, it was first introduced by Rocklin. Maybe I'm not writing it the Russian way. In 1960, I think, and the paper is called Exact Endomorphisms of a Lebesgue Space. Okay. So as he mentioned, the natural extensions are unique up to isomorphism, and they basically have the same dynamical properties as the original one. So ergodicity is preserved, mixing and entropy. Yeah. Okay, so let's go to the examples. Some will be very simple. And let's find the natural extensions of these examples. Okay, so the first example, which was very simple, these are the expansions with integer base. So, so sometimes call them M-adic expansions, but they are expansions to integer base. And let me, for simplicity, the same analysis works for any M. So let me take M is 2, which means I'm looking at the binary expansion. And as we saw, these are generated by a very simple map, which is the 2x modulo 1. So this is the original system. And now my notation is a bit weird, because here I'm calling T the invertible one. And I usually call T my maps. So this is my S in this definition, but I'll call it T. And this is the map. 2x and 2x minus 1. And here half has two choices, but I'm going to make this choice, so I'm going to open it in half, which means half gets digit 1. Usually you open it also at 1, because we don't want to look at the expansion of 1. Okay, and so this map, if you iterate it, you generate expansions of this form. And the AIs are zeros or 1, depending if you are in the ith iterate, if you are in the 0 region or the 1 region. And so in this way, this means I can actually identify X with its digit. So you can identify points X with the one-sided sequences of zeros and ones, which are just the binary digit. And this identification is well-defined, unique, except for the dyadic rationals. As we mentioned, points of this form have two expansions, some ending with zeros or ending with 1. Like a half, I can write it as just a half, or I can write it so so the corresponding sequence will be 1 and then followed by zeros, or I can write it as zeros followed by 1s. But because of my choice here, I put half in the 1 region. This expansion I don't see in my iteration. I actually see this form. So if I make this choice, that all the dyadic rationals have finite expansions, then I can also make this identification that I send a dyadic rational to the sequence ending with zeros. And so it is surjective almost everywhere, because sequences ending with a tail of 1 have measure 0, if I have half-half product measure. Okay, so the natural extension, you expect it. So here I have like a full shift, okay, except for this tail of 1s. And you expect the natural extension to be two-sided shifts. And that's exactly what we're going to see. But what we like is a geometric representation of the natural extension. And the natural extension is just the well-known, what we call Baker transformation. So the space of the natural extension here, okay, let me call it X, is just 0, 1 squared. And I have the product Borel sigma algebra, or if you like, do Lebesgue. As I said, in the context of ergodic theory, it doesn't matter because they just differ by sets of measure 0. And I'll do product Lebesgue measure. Let me just do lambda bar, so it's lambda cross lambda. So it's two-dimensional Lebesgue measure. Okay, so this is just the space, and now what's the transformation? Let me call it cal t. So this is just 2x y over 2 if you are less than a half. If x is less than a half, and it's 2x minus 1 and y plus 1 over 2 if x is greater or equal to half. And actually, what you see on the first coordinate is just my t, and what you see on the y coordinate is the missing digit. So in fact, this is like y plus 0 here. So you see, if you are less than a half, then your first digit is 0, but when you do 2x, then you've lost this 0, and you put it in the y coordinate. And here it's 1, and when you apply your map, you sort of lose it, and you get a half. Maybe one more thing. If I make this identification here, let's go back to the one-dimensional case. If I make this identification, then t can be seen as a shift. So if this is the sequence associated with x, then the sequence associated with tx is just a2, a3, etc. So you can see every time you apply t, you lose the first digit, but the natural extension keeps track of it and puts it here. So in fact, I can, if you like, write the natural extension in this way as, let me write it here, the txy in one formula as tx, and then here I have y plus my first digit, of course, it depends on x, divided by 2. Cal t can be seen as a two-sided shift. And how can you see that? Simply by maybe I should have raised the board. So if I express or identify x with its binary expansion and also y with its binary expansion, then I can see the point xy. I can identify it with the following two-sided sequence. So on the right, I put the expansion of x. So this is the binary expansion of x. And on the left, I put the binary expansion of y, but let me put it this way. So this is the binary of y, and this is the binary of x. And this is like my 0th coordinate. This is where my window is. And if I apply t, then I'm simply moving my 0th coordinate to here and putting this in the past. So this becomes a2, a3, etc. And the a1 goes on the y side. So you can see exactly that t is a two-sided shift. It's two-sided full shift. Because after any digit, I can see 0 or 1. So there's no restriction. OK, so if we verify these three conditions, maybe I'll raise the board. Then the map C is actually kind of clear. So now C is just a projection in the first coordinate. And it's quite clear that 1 is satisfied. because if you do this identification, maybe it's the easiest thing. So if I have, this is my point x, y, now I see them as sequences. Here's my zeros. And if I apply c, then I'm just seeing the x part, so I'm just seeing a1, a2, etc. And then if I do s, my notation is bad, so the s is my t and the t is my cal t. So if I do my t, then I just shift and I get a2, a3, etc. And so this is the right side there. And if I do the left side, so if I start again with this point, and if I first apply cal t, then I put this here. Like this. And if I do c, then I'm just projecting in this part, so I get a2, a3. So you can see the commuting kind of easily. And 2 is also easy because both are Lebesgue measure. And so let me do 3. So let me just verify 3. Okay, so now the G is the Borel, the one-dimensional Borel, and F is the two-dimensional Borel. So basically, I want to prove this, that B cross B is the smallest sigma algebra generated by the following, that I pull back my, my Borel sigma algebra, so it's actually B cross 0, 1. This is actually C inverse of B. And then I move it around like this. So I want to prove this equality. Now, clearly, the right side is a subsigma algebra of the left side because C is measurable, so this sits in B cross B. T is measurable, so this is also in B cross B. And so since each one is in B cross B, so also the join is there. So this is clear. And to do the other side, all I have to do is that the generators of B cross B are in here. And since this, yeah, so that would prove it. Now, B cross B is, in fact, is generated by the cylinders that we talked about last week, and also Valerie and mentioned them quite often. Namely, by these cylinders, so I'll call them delta K1 up to Kn cross delta L1 up to Lm. So in here I'm specifying the first n coordinates of x, and here I'm specifying the first m coordinates of x. So I need to see that these guys are in here. And in fact, if once we see things as shifts, as full shifts, it's not hard, because let me just do one thing. If I do t of such a, okay, so I take this, so now I take a cylinder in my x coordinate, and it's going to be Lm up to L1, K1 up to Kn. So I look at this cylinder where I'm specifying the first L plus m coordinates of x. And if I do, and then I lift it up, so this sits in here. And now I lift it up, so I do cross 0, 1. And then if let me just do t one time now. If I do t one time, then what it does, t takes the first coordinate and puts it in the y coordinate. So in fact, this is delta of Lm minus 1 up to L1, K1 up to Kn. And I've moved Lm here, so now I'm specifying one coordinate, so I get delta Lm. And if you do it another time, then you move this Lm minus 1, you put it here, etc. So if I move this m times, then all I'm doing is I'm taking these digits, putting them on the y side. But you know, they get reversed because first you move Lm and then you move Lm minus 1, etc. So you get exactly this cylinder. So indeed, the generators, that is the product of these kinds, are obtained by lifts of cylinders in the x space and moving it around appropriate number of times depending on how many coordinates you're specifying. So all the generators of B cross B are in here. And that gives you the equality. Okay, so that's kind of simple. Now let me go to the second example, which is the Luroth series. And as I mentioned last time, they belong to the same family because they're made of full lines. So let's do that. I'll take the paper so I don't forget. Okay, so let's go to the Luroth series. And both of these, the binary, the Ergodic, and the Luroth series, can be identified with full shifts. So all the proofs are really the same. The only difference is the number of digits. In the binary, we have 2 digits. In the Ergodic, we have m digits. And here, we have countably many. So the map here was Tx was n plus 1x minus n. If you are in 1 over n plus 1, 1 over n. So this is like a linearized version of the continued fraction map. Etc. So all these maps are full. So this is, if n is, let's see, 2 in this case. So it'll be 2x minus, so I should know this, 2x minus 1. And this is 6x minus times 2, 6x minus 2, etc. Okay, and as we mentioned, I get expansions that look like this. So sums of inverses of integers. Like this. Okay, and here we saw also that Lebesgue measure is the invariant measure. Okay, and we can do the same thing, in fact. We can also identify x with its digits. So I can make this identification that x just is identified with A1, A2, etc. But now all the AIs are in 2, 3, etc. So it's a full shift on countably many digits. And T behaves exactly like the shift. So if this is the identification of x, then the identification of Tx is just A2, A3, etc. And the natural extension looks also similar to the binary. That is, the missing digits you have to put on the y side. And so the natural extension the domain is also the unit square and the Borel sigma algebra, the two-dimensional, and also two-dimensional Lebesgue measure. And the transformation is, as I said, captures the missing digit, so it looks like this. So here I just do the Tx, and by doing this I'm actually losing the A1 part. And so I want to put it in the y coordinate. And then I do this. This is a 1 over A1. That's of x, of course. And then the y part, I I divide it by a1 times a1 minus 1. And I can see also this as a two-sided shift. Because if I make identification like I did before, so I do the Luroth of x here. So let me just write down the digits. So this is the Luroth of x. And the Luroth of y, if I write it with a b, etc., like this. And I want to put the missing digit on the x part, and you can see what I've done. I just multiplied by 1 over a1 minus 1. So now this part will have a Luroth series that starts with okay, so I'm missing the first one. So it was 1 over b1. So I'm dividing everything by this. So you get, so I have the 1 over a1 here. I gained this 1 over a1 from the x part. And then I am, these become in the second coordinate. So I have a b1 here. And then I'm multiplying by a1 times a1 minus 1. So this is the second one. And then I get the rest are also the same, but multiplied by this factor. So what I'm saying is that all I'm doing is that if I identify x with its Luroth series and y with its Luroth series, like this, then t of xy, I will get a series where this gets here. So it's again two-sided shift. And the verifications are exactly the same. Exactly the C that is in the definition of the natural extension is just a projection in the first coordinate, and the verifications are identical. Yeah, the only difference are now I have countably many digits. Before I had only finitely many. Okay, so these are really nice because it's like a geometric representation of a natural extension, and everything is very clear what the what the behavior. Okay, so now I want to go to the third example, which are beta expansions, and these are not as simple as this. And the reason why is that here we have full shifts, and the natural extension, the beta expansions, we don't have a full shift because not every sequence is allowed. So what I want to do is first start with a simple example where things, or simple case, where things are clear, and then I'll go to the general case. The first examples can also may be interesting for people in tiling, but the general case is not. Because for tiling, people look at piezo. And if you don't have piezo, then you have problems with tilings. But still, we can write down a natural extension that might not look very nice, but still we can get a geometrical representation. Okay, so let me look at beta expansions. So this is the third example. And first I'll start with let me put 1 here. I'll start with a simple case. So I'll start with a multi-node sheep, but sometimes we call them pseudo golden mean because they all behave the same. And sometimes, actually, me and Coro, the only people refer to them as pseudo golden mean, but it doesn't matter. Okay, so I'm looking at betas that are solutions of the following polynomial. So let me just write it down, that beta satisfies beta to the n is beta n minus 1 plus beta n minus 2 plus beta plus 1. And you can look at these all So I'm looking at actually the positive root of the polynomial defined by x to the n minus xn minus 1, etc., up to minus 1. And this is piezo, so all, so if you look at the polynomial, this one, so all the other roots are less than 1 in absolute value. And they all lie between 1 and 2. And so I only have 2 branches. And I know that last time I increased my domain, but now I want to go to 0, 1. And in the second part, if I have time, I thought I might finish early, but I'm not sure. I will extend my domain again. So they all look like this. Just one branch, sorry, 2 branches, one full and one not full. And so if you look at the greedy expansion of 1, if you look at, usually we open it at 1. And the reason is because 1, nothing gets mapped to 1, because here I open it here. So nothing gets mapped to 1, and that's why we remove it from our domain. But still, we talk about the orbit of 1. So the greedy expansion of 1 that is, if you look at 1 and iterate it under this map, is finite. So that is, 1 can be written as 1 over beta plus 1 over beta squared up to the degree, like this. And you can see that the orbit of 1 is finite. So T1, which means I multiply by beta and subtract 1, because 1 lies in the 1 region. So the map is beta x minus 1 here. So then you get 1 over beta plus, and you start getting 1 power less, etc. And up to n minus 2, I think. And minus 2, 1, you come out with 1 over beta and Tn minus 1. Let me think. The golden mean. Is it true? 1 goes to 1. And this is 1t, and this is squared is 0. Yeah, okay. So Tn, no, sorry. So this is n minus 1 is 1 over beta, and Tn of 1 is 0. So I have a finite orbit. Okay, and the natural extent, the invariant measure here is not Lebesgue, as we mentioned before. And as I mentioned, Perry and got it in the 60s, and Galfin got it in 59. But Perry was not aware, I think, of Galfin's result. But with a natural extension, you will see another way of getting it, in fact, of getting the invariant measure. It looks, in this case, it's finite, so it would look like this. So invariant measure, let me call it mu. And there is a normalizing constant just to make things a probability measure. I call it f of beta. And then here you have some. In this case, it will be finite. So it will be the indicator function. People could call it chi, but in probability, we use it 1. So I'm used to you doing 1. I think m minus 1, maybe I start with 0. N, yeah, divided by. So this is the invariant measure, and it's equivalent to the Lebesgue measure on 0, 1. Yeah, okay. And the natural extension looks like this. I'll get my paper. It's going to look like a ladder. It's not a square anymore. So the underlying space, okay, maybe now it looks a little bit abstract, but I will make a figure. Everything depends on the orbit of 1, really. In my notes, I have m is n, so I'll have to be careful. Okay, so it looks like, let me do m is 3. So it looks like this. My scale is bad, but that's okay. So here's 1 over beta. So that's t squared of 1. And this is 1 over beta plus 1 over beta squared. So here's t1. And here's t squared 1. And t cubed 1 is 0. And here also I have 1 over beta. So in this description, I am giving these squares. So this is when m is 0, k is 0, and then I'm doing this and this. So I have 3 parts, and I'm writing them vertically. That's why they look like this. And I will take here, it's the restriction of Borel on X. So let me just do B cross B intersection X. And also Lebesgue measure, normalized Lebesgue measure on X. So let me write it here, normalized Lebesgue measure on X. So, because I just want to make things probability measure. And what's the transformation? Maybe I'll erase it. Okay, the transformation basically looks like the Ergodic and the Luroth series. So it looks like this. T xy is equal to, here you do the beta expansion in the first coordinate. And in the second coordinate, you want to put the missing digit. So this is y plus, the first digit of x, it can be written as the integer part of beta x. This is the first digit. And then you divide by beta. So, and this works because in this, if I'm looking at the Multinacci, where is it there? Then no two, so in here, we don't allow n ones in a row. So blocks of n ones are not allowed. So we have what we call subshift of finite type. But still, if I write the beta expansion of x and I write the beta expansion of y in reverse order, then everything is allowed because this is what we call palindrome. So if you read it forward or backward, it's the same rule. And how does this behave? Maybe I'll draw the figure again. Let me do it 2 times. So the way it behaves is this part here goes here, and this part here goes always look at my drawing. Here we go. Goes up here. And this part here goes here. And it's very clear that this map preserves Lebesgue measure. Why? Because basically T multiplies by beta, so you expand with a factor of beta, and the y coordinate shrinks by a factor of beta. And so they cancel each other, and you get Lebesgue measure. Okay, so this is the natural extension, and the verification also is basically the same. As I mentioned last time, you can work with full cylinders, that is cylinders corresponding that get mapped. So if I have a cylinder of length n and it's full, this means Tn maps it to the whole interval. you can work with full cylinders, and with full cylinders you can do the same verification. That is, if you take product of two full cylinders, then they are obtained by lifting a bigger cylinder down, up, and doing t n times or m times, depending on the number of coordinates. Exactly the same thing I did for the binary. Okay, so for these guys, for the multi-Nachi, we have a nice domain. Now we try to do this for general beta, or even for algebraic betas, and as Pierre mentioned, the problem is you can always use this formula. This is good, but the problem is find the right domain that things map bijectively. And it was incredibly, it didn't work. So we had to do another thing in order for it to work. So let me talk about the natural extension in general. You can also make it look like a ladder, but the ladder is not symmetric. That is, I don't mean symmetric, I mean that this is shorter and then this comes here. So you can stack, so they are not, sometimes you have to jump a little bit. So let me show you how it looks like. Now, instead of stacking things on top of one another, like here, we put them in a disjoint way. So let me do the general case of the beta expansion. And again, it depends on the orbit of one completely. But, yeah, okay. So this is the domain. So the domain, okay, before I write down the domain, I'm going to tell you about the pieces. So we have infinitely many pieces, actually, or finite, depending on the orbit of one. But anyway, so we have R0 is the unit square. And then, because I want to put them in a disjoint way, so I'm going to also put, I'll put it later. And then Ri is 0, the Ti1, the orbit of 1. And then I cross it with 0, 1 over beta to the I. So my heights get shrunk every time with a factor of 1 over beta. And my underlying space X is the union of the Ri's crossed with I. Because of course, these intersect, but I want to see them as disjoint pieces. So I'm going to put an extra coordinate to see them as separate pieces. Again, this might be finite if the orbit is finite, but let me just, so they will be, so if the orbit of 1 is finite, then this will be 0 and this will be an empty set, okay? So that's why it's okay if I do this. Okay, and then the sigma algebra is just disjoint union of the Lebesgue sigma algebras. So each one gets its own sigma algebra, Lebesgue or Borel. And again, lambda bar is going to be normalized Lebesgue measure. Okay. And now what's the transformation? So I'm going to see these like this. So here's R0. And here's R1. Depending on, I don't know how long it is, depending on what T1 is. And here's 1 over beta. And this is the next one, maybe like this. 1 over beta squared. Let me do another one. Maybe the other one is a bit longer here, but thinner. And etc. So this is my space. And my transformation now these are like, I'm going to move through these if I'm non-full, and then once I'm full, I'm going to go back here. So I need some preparation. So just to be exact, let me write d star of beta as b1, b2, etc. So this is just a shorthand. This is really b1 over beta plus b2 over beta squared plus b3 over beta cubed. And this is equal to greedy expansion of 1 if the expansion is infinite, and it's equal if the expansion is finite, I need to make it infinite. So I do, it's d1 dm minus 1 and then dm minus 1, and this is repeated if expansion of 1, if everything is greedy, if expansion of 1 is just d1 up to dm. So if the expansion of 1 is finite, then I adjust it like this. This is also equal to 1, and actually this is, some people call it quasi-greedy. So you just make it infinite by making the last digit minus 1 and then repeating. It also equals 1. Okay, and the expansion looks, the transformation looks like this. So now I have 3 coordinates. The I is for, so this is actually cross 0 and this cross 1, etc. Etc. So this is equal to, here it's always in the first coordinate I do tx, the beta transformation. And then I send y to y star. I'll tell you what y star is. And I go from level I to level 0. This is to R0, in other words. If the first digit of x is less than the ith plus 1 digit of this guy, of d star plus 1. So in other words, let's do here. So in T1, I will be T1. So the last thing here is B1 over beta, B2 over beta. So if I am to the left of this line here, this means I am with the full lines. So I go back here. Wait, so okay, let me write it down first and I'll make a figure. And if I am equal to the last digit, equal to Bi plus 1, then I go to the next block. And now I star will have, has 2 definitions depending on these conditions, like this. Okay, so let me just write down and I'll show you with the figure what I mean. Okay, y star equals to, so if you are less than the ith plus 1 digit of 1, then I go back to the R0 rectangle and I put all my missing digits. So these are like memory. If I am here, this means I'm not full, but I know that I come, okay, so in other words, if I am to the left of B1 over beta, that is, I'm in the full section, then this rectangle gets mapped here. And this is now, so this part goes here. Now, if I am in this part, then I go back to R0 and I get stacked somewhere here, etc. And if I'm not full, that is, if I am this part, then I go to the next rectangle. And depending on my position, if I am less than B3 over beta, then I go back to R0 and I get stacked horizontally all the way through. Otherwise, if I'm in this part that is non-full, then I go to the next one. So y star is equal to, if I am in the ith rectangle, then this means my expansion really began with the same expansion as 1 in the first I digits. And then I put here the A1 of beta, and then y over beta, if a1 is less than bi plus 1. And if I am equal to, then I have to go to the next rectangle, and I just shrink my y by beta. And what I'm saying is exactly what I tried to say here. So if you are in R1, it's like a waiting station a little bit. This means that originally I began here. So my first digit is B1, so I go to this. If I am full, then I'm ready to go back to R0, and I remember the B1, and I also remember my next digit, which was A1. And if I'm not, then I keep going to the next rectangle. So this is really the natural extension, and you can, I don't want to go through the verification because it's a little bit cumbersome. But anyway, this is the natural extension. You can also, if you like, stack these on top of the R0, all of them, so you get another sort of version that looks not as nice as the golden mean case or the Maltinacci. The stacking might be like this, and then might be the next one bigger, I don't know, depending, and like this. So you can also get a ladder, but not a nice ladder. Okay. But maybe I was, if you look at Lebesgue measure, and if you project in the first coordinate all of these little rectangles, you get exactly the Perry formula. Yeah, here I wrote it in a finite case because I was looking at the Maltinacci, but in this case you get exactly this infinite sum. So this gives you another way of seeing the invariant measure. Okay. So let me now go back to continued fractions. I just want to show you one other application of why natural extensions are nice. Now, Pierre talked about, as we said, natural extensions are unique up to isomorphism, so there are many versions. If I'm not mistaken, Pierre looked at another version. So I'm looking at continued fractions, so this is 4. And the map is that Tx is 1 over x minus integer part. And Pierre, if I'm not mistaken, wait, and here the invariant measure is, this is a normalizing constant, we like that, u of a. And the density is 1 over 1 plus x. Here the x is Lebesgue measure. This is the invariant measure. And Pierre looked at this T tilde had this space. So this part here. And he indicated that normalized Lebesgue measure is invariant here. And then he mentioned at the end that you can make change of coordinates and get another invariant measure, another version. And this is the version I like to work with. My space now is a box. But my invariant measure is not a Lebesgue anymore, but it has a density. So and his formula was a bit different also because his domain was different. So my version looks like this. So here we have the continued fraction. And so, of course, we have the 1 over a1 plus 1 over a2, etc., which can be identified with a shift also. That is, you identify x with the digits. And if you do t, then you've lost a1, and you want to capture it back. And you capture it here, like this. And this, of course, is just entier 1 over x. So this is my version of the natural extension, not mine, but the version I work with. And the invariant measure, let me call it mu bar, And now C is a two-dimensional Lebesgue set here. And the density is now is 1 plus xy squared, dy dx or dx dy, doesn't matter. And here I have a normalizing constant, log 1 over log 2. So this is a natural extension of the continued fraction map. And in fact, if you project to the x coordinate, that is, you integrate with respect to y, then you get exactly 1 over 1 plus x. So you get the invariant measure on the or the Gauss measure. But I want to mention it because you can also get information about the quality of approximation. So I'm going to write a few things that Valerie wrote, so I just write them down because she did them. Of course, the Pn over Qn are the rationals approximating x, and they are obtained by just truncating up to n, level n. And there are nice relationships between how, if I look at x minus Pn over Qn, and Valerie wrote them down, so I'll write them again. This you can write as minus 1 to the n, and then here the nth iterate of the Gauss map, and then you get here Qn, and then Qn plus Qn minus 1 Tn. So there is this nice relationship. So the map really gives you information about how far x is from its approximation. And people like to normalize this so that it lives between 0 and 1. So this is what people call theta n of x, so approximation coefficient is it people call it. And of course, you usually look at the distance, so you put absolute values. And I want to make it between 0 and 1, so you multiply by Qn squared. So if you do this in absolute value and multiply by Qn squared, then you can rewrite this as sorry, Tnx over 1 plus Qn minus 1 over Qnx, Tnx, like this. And this guy is really nice because this captures the past. In fact, Qn minus 1 over Qn, let me just write it down, is if you iterate x t n times, then you're losing the first n digits, and they are in here, but they're written in reverse order. So this cues capture the missing digits, and so and then okay, so you can write it like this, and then you can wait. Yeah. So if you start with the with x0, and you start looking at the natural extension, the nth iterate, then what you're really getting is just here you get T and X, and here you get these QNs. But this is the orbit of points on the x-axis. Okay, and now there was a conjecture that was hanging around for a while. It's called Dublin-Lenstra conjecture. which is related to the thetas, distribution of the thetas. Actually, not really, but that is, the conjecture said that the limit as n goes to infinity of 1 over n, if you take the average of the thetas, that this converges to the following. That's equal to z. It's linear if you are less than a half, and then curves greater than a half. You have this formula, 1 minus z plus log 2z. Hope I'm right here. If you're greater than a half. Okay, so this was a conjecture, and in yeah.
What is z equal to x?
Oh yeah, that's not right. What I'm writing. Oh wait. Yeah, because I am writing it wrong, because I meant this, the following. That's why it's distribution, sorry. So I meant, for any z, the limit as n goes to infinity of 1 over n, and here you count how many times I between 1 and n, for which theta I x is less than or equal to z. This is where the z comes in. So you count how many times are your thetas less than or equal to z. Yeah, this is what it is. Yeah. Okay. And now in 683, Jager, Boesma, and Wiedijk gave a proof, and the proof is really natural extension, and it's really very simple. So let me show you what it is. Okay. Okay. So so I'm going to define. Look at the. You see the thetas. I didn't say that here. Okay. These things, this is the theta, and if you see, this is the t and x, so it's coming in the first coordinate here, and the qn minus 1 qn is coming in the second coordinate here. So this is like, I can obtain this expression as a function of this guy. So I'm going to let a sub z to be the set of all points in 0, 1 squared, for which x, that's like playing the role of t and x here. I'm going to iterate, but that's the starting point. And then I have 1, and this is going to be like the second coordinate because it's appearing here, so I'm going to call this y. X less than or equal to z. So I look at this region, and if you look at the, I erased it, but this is the invariant measure of the Gauss, two-dimensional Gauss. If you look at the mu bar of AZ, you just apply this formula, and you see what you get is exactly the f that I'm looking for, this function. Let me call it fz. Let me call this fz. Yeah? And now, and then you see that theta j of x is less than or equal to z, is exactly the same, and that you can see by connecting the formula for theta and this expression here. It's exactly the same as saying that the jth iterate of t of the point x0 lies in AZ. problem is, so this means that if I want to look at 1 over n, the frequency of the times that my thetas are less than z, this expression that I'm interested in, then I'm actually doing the ergodic average of the indicator function of AZ applied to the point Ti of x0. Okay. And then you say, okay, ergodic theorem. But here you have to be careful, because the ergodic theorem is an almost everywhere statement. You know, the ergodic theorem says that if f is an L1, then 1 over n sum ftix in general converges to the integral mu almost everywhere. That is, not every point is generic for the measure mu bar. So so x0, I don't know if x0 lies in this good region where the ergodic theorem works. But then Jager in 86 showed that the orbit, or let's say, showed that x0 is generic for the ergodic theorem. That is, it's in the good set when f is the indicator of AZ. It's generic for ergodic theorem. Let me write just ET applied to indicator AZ. In other words, taking limits here will converge to the right thing. So by Jager, if I take the limit, this goes as n goes to infinity, indeed to the integral of the indicator d mu bar, which is just a measure of mu bar. And that's the f, and this is exactly the formula we're seeking. So you can see that the natural extension also has, it can be used not only to get invariant measures, but also to, like here, to gives, if you like, distributions of approximation coefficients. And you can also look at 2 consecutive ones and things like this, but I don't want to talk about it today. So let's see, I have 5 minutes. Okay, so in 5 minutes, let me move completely to another subject and just give you an outline of some stuff on how to deal with the multitude of beta expansions. So maybe I'll raise this to keep it on the board. Just give some outline. I will not talk much. Okay. Now, when I talked about beta expansions, I mentioned a few times that there are uncountably many possibilities generically for almost every point. And I gave 2 algorithms. One is the greedy that we've been talking about. Another one is the lazy. So beta expansions again. But now with beta expansions, I mean any expansions in, there is any expression of this form. Not necessarily greedy. With the AIs, I'm also going to look at specific digit set. You can do everything with a general digit set. The same analysis, but then you have to be careful because not everything can be expanded, and then you have to put conditions on your digit set. In any case, so let me look at this case. And I mentioned 2, let me do a beta is 2, anti-beta is 1, just for simplicity, which means beta lies between 1 and 2. And I want to take it non-integer. Okay. So this was the greedy. Now I want to expand my domain of definition. So I want to go to 1 over beta minus 1 because this can be expanded also. So here, in this case, my digits are 0 and 1. So 1 over beta minus 1 is captured by doing 1, 1, 1, 1, 1 all the time. And so here's, let's say, 1 over beta. And this is beta x, and this is beta x minus 1. And usually 1 is somewhere here, I don't know, like this. So if you use this map, you get, and this is region 0 and this is region 1, this gives you greedy expansion. But if you do this, let me remove this. Okay, let me make another figure and then I'll put them on top of one another. So here what I've done is, in case beta between 1 and 2, I took one interval of length 1 over beta and left the rest as it is. And now if I do the reverse, I start with the right endpoint and I do 1 over beta here. And I do this. I get also here beta x and here beta x minus 1. If I iterate this map, I get lazy expansions. That is, at every stage you use the smallest digit you can. So here I'll use 0 as long as I can. And here I want to do things greedily, so I use 0 if I have to use 0, and then if I can use 1, I will do 1. That's why I stop here. Okay, so now if I sort of put these on top of one another, then I get this figure. Here's 1 over beta. This point here isn't, sorry, this is not right. This distance is 1 over beta. But this point is 1 over beta, beta minus 1. I get this figure. And as you can see, there is this interval where I have a choice between the two maps. In here, in this part, I have no choice. I have to use beta x. In here, I have no choice. I have to use beta x minus 1. And in here, I can make a choice. I can use beta x or I can use beta x minus 1. If I do this, then I'm using a lazy choice. If I do this, I'm using a greedy choice. So you can get other expansions in two ways. You can either do it deterministically or randomly. Deterministically means simply taking this region, divide it into two parts, whatever choice you want. If you want to get some results, usually you divide this into two intervals, and you say on the left I will do greedy, on the right I will do lazy. And if you do this, then you can actually identify this choice with the transformations beta x plus a modulo 1, also stated by Perry. And if you do other choices, the dynamic, maybe the dynamic would be more difficult to explain. But what I want to concentrate on is now like a random choice. So in this part, I want to flip a coin. If I get heads, I want to use greedy. And if I get tails, I want to use lazy. And if I do this, then actually this will capture all possible beta expansions. So what I'm talking about is I can still describe a transformation, but on a bigger space that captures all expansions. So, okay, let me enlarge my space. So now this omega is my coins. 1 is heads, 0 is tails. And I want to use it in an efficient way, only here. So if a point is here, I don't want to use a coin. If a point is here, I don't want to use a coin. If here, I want to use a coin. So now my space looks like the coins times the interval where I do the expansions. And my map is big one, so I'm going to call it K. It maps this space to itself. And the way it is defined, omega will correspond to a coin, so infinite sequence of zeros and ones. And X is the point I want to expand. And it is defined as follows. I'm going to just write it down, but its description is what I just mentioned. These I call the regions where I have no choice, I call them E for equality. The two maps have the same definition. So this is E0, and this I call E1 because I'm using digit 1 here. And this I call S because I can switch between the two. So if I am if I am in E0, then I don't want to use the coin. So, of course, on this we always can do shifts. So I keep the coin as it is. I don't flip. And in here I use the map beta x. If I am in E1, I also don't use coins. And I do beta x minus 1. I have to. And if I am in S, I flip a coin. So in here, maybe another one, I flip a coin, and if the coin I flipped, that is the first coordinate of this infinite sequence, is a head, then I use the greedy, so I use beta x minus 1. Because I flipped the coin, so now I shift my coins tosses, because I'm to be ready for my next entrance. And here I do beta x minus 1. And if I get a tail, if I am in S and I get a tail, then I use the map, the lazy map, which is beta x. And since I use my first coin toss, I will shift like this. So this map describes exactly what's happening here. Let me just mention a few things because I'm out of time. So this map, K generates all beta expansions. And also with this figure, you can, some points have uncountably many, but there are cases where you have one expansion or you have finitely many. And you can also see this in a dynamical way. I get unique expansion if when I apply, when I take an x and let it move around, I never hit S. So unique expansions correspond to points whose orbits never hit S. I have two expansions if I hit, that's not really right. Okay, if I hit S once and then never hit it again, etc. So you can so you can give a dynamical descriptions of the number of expansions via this map. And you can also look at ergodic invariant measures and study with respect to these measures the distribution of your digits and things like this. So I think I'll stop here. It's getting too late. So that's it. Yeah.